So I cannot say that I'm happy to be here because after all, we are in a memorial and we all have fond memories and almost everything could be said already about Krzysztof has been said in the last few days, so I will not add much. I just want to say that the other person that I knew well, in fact, at the University of Chicago, that reminds me very much of Krzysztof was Chandrasekhar. And why I'm saying that they remind me of each other, because of this facon of modesty. Also, Chandrasekhar was very modest, very, not self-depreciating, I would say. But every now and then there'll be a sword coming out of smartness and cynicism that reminds me very much of Krzysztof. That I like very much. When I think about Krzysztof, I actually smile because he had this capability of catching you at the right moment with the right remark. Really, really very wonderful. But as I said, a lot has been already said, so I'll not take much time. We are losing some of our friends, and this is sad. I guess for me, it's coming out of age. I'm really losing all my best friends, Leo Kadanov, Mitchell Feigenbaum. So, we will have to continue to survive and do good work. So what I want to discuss with you today is work that I have been doing in the last couple of years, 3 years, 4 years. And let me start by telling you that in a paper that was uploaded in the archive recently, I read the following. From the point on about amorphous solids. Now, amorphous solids, you may or may not know what we mean by amorphous solids. These are glasses. These are systems like sand, systems that are actually acting as a solid in the sense they have a finite shear modulus, but don't have a long-range order, and are not typical solids that have a well-defined equilibrium configuration. And this is what I read in that paper, that from a point of view of elasticity, a glass is a very simple solid, elastically isotropic, described by a density rho, a bulk modulus B, and a shear modulus G. Consequently, one has isotropic, longitudinal, and transverse sound velocities, VL, VT, respectively. This is no problem. Well, I think that rarely one sees such an optimistic thing that is truly wrong. And let me tell you why this is wrong. In fact, we know that in the thermodynamic limit, when the system goes to thermodynamic limit, plasticity in amorphous solids sets in immediately. This is not true in regular solids. Also, regular solids, like crystals, if you push them hard, at the end, there'll be some plastic deformations. But for small strain stresses, this is not the case. They really react elastically. And there are many books, Landau Lifshitz and others, that describe elasticity theory for such solids. For amorphous solids, any amount of strain will end up with having plastic deformations I'm going to describe and discuss with you in this talk. We know this already for more than a decade, and it's accepted. Now, typically, plastic events exhibit quadrupolar symmetry. This is important, and I'll explain. You know very well in electrostatics, for example, there are charges, monopoles, and there are dipoles. Charges cannot form spontaneously. There is a conservation of charges, but dipoles can form. So a dielectric, what is a dielectric? It's a material that you put an electric field on, and then molecules will polarize, right? They make dipoles. And dipoles have an importance in dielectrics because they dress the dielectric constant, they renormalize the dielectric constant, but they don't change the form of the theory. They say parallel interactions are still there. Charges, on the other hand, which cannot be formed spontaneously, they have to be there, like ionic solutions, they change the structure of the theory. You have Debye screening, you know about this, and things turn from parallel to exponential decay. In elasticity, it turns out that monopoles and dipoles are protected, but quadrupoles can appear. This quadrupole is a plastic event that locally releases strain by some particles going out, some particles coming in. Okay, so it's a quadrupolar structure that has been already discussed by Eshelby in the 50s. Now, plasticity, as I'm going to explain to you, has profound effects, and let me tell you what is the upshot of this talk. It's for small amounts of plasticity. Classical elasticity remains valid in form, but the elastic moduli get rest. There's screening by the quadrupoles. This is the, if you want, the equivalent phase to dielectric in electrostatics. However, when you have a large densities, high amounts of plasticity, elasticity theory is modified, and then you get screening by dipoles. And dipoles, I will explain how they come about, and the dipoles change the physics entirely. And this transition from screening by quadrupoles to screening by dipoles is analogous to other phenomena that people know about, like the Kosterlitz-Towless and the hexatic transitions. I'm sure that all of you heard about this, but let me nevertheless remind you what are these transitions. For example, hexatic. Hexatic was discovered by our friends in Harvard, David Nelson, Bert Halperin, already many years ago, about the melting of two-dimensional solids. Now, two-dimensional solids generically have hexagonal structure. So you have hexagons. At zero temperature, perfect crystals. Now you increase the temperature a little bit, and two hexagons will melt and will make unstable pentagon-heptagon, but this is going to fluctuate. Pentagon, heptagon, heptagon, pentagon. Heptagon, pentagon, and this is a quadrupole. The quadrupoles that you're going to see there, which form at a given temperature, they soften the solid, the moduli decrease. Nevertheless, it doesn't change the form of no symmetry has been broken yet in this process. You go to a next temperature, critical temperature, and then two hexagons that made pentagon-heptagon, it becomes stable. These are dipoles. The dipoles are changing the structure of the theory entirely in the sense that they break translational invariance, and then you get to a new phase where there's still hexatic order, but not long-range order. And this is the hexatic phase that has become very famous. And only later, when temperature reaches the melting point, these dipoles, the pentagon-heptagon, separate into independent heptagon and pentagon, which are really monopoles, and the system melts. So they discovered an intermediate phase in the melting transition between the solid and the liquid, which is the hexatic. Similarly, Kosterlitz-Towless transition, again, you form a dipole, you form dipoles, and in this situation, you break translational symmetry, and there is a new phase. Let me also state that both the hexatic and the Kosterlitz-Towless exist so far only in 2 dimensions. And the reason is obvious. For hexatic, simply you don't have hexatic crystals in 3 dimensions. For the Kosterlitz-Towless, it's less trivial, but still clear. A dipole in 2 dimensions has an energy that is logarithmic in the system size, but you have so many places to put it, so the entropy, the number of positions also grows with the system size. The entropy is the logarithm of this, so you have a compensation between the entropy and the energy of the dipole that is no longer the case in 3 dimensions, because in 3 dimensions the energy of a dipole is not logarithmic. Okay, so now, respecting the consent of time, I will describe the new approach that we are developing now with a very simple setup of an amorphous solid that is confined to an annulus of radius Rin. Okay, so you have here the Rin. This is a little cavity here, a radial cavity, and R-out, which is this blue thing around. In the middle, we put an amorphous solid, which in the experiment, this by the way is an experiment that we did with our colleagues in China, Zhejiang. And you have here disks of 2 sizes, and you choose the 2 sizes such that there is amorphous structure. It doesn't fall on a crystalline solid. And the trick is going to be that we're going to inflate the inner radius. So in the experiment, they have a little gizmo here that they can pull, and when they pull, this radius changes to the Rin to Rin plus some correction, some D0, so you push from the inside. By the way, let me say that this is not chosen in random, because majority of work in the last decade on amorphous solids was for simple shear. People are talking simple shear or pure shear, which is the worst way to see what I'm going to tell you today, because I'm going to argue that the strain should be non-uniform in order to see the transition that I'm talking about. In simple shear or pure shear, the straining is uniform over the whole system, and we'll come back to that issue. Okay, and then what happens? We then impose the displacement that you just explained. Oh, I'm sorry. So the displacement is such that the displacement is radial and of size d0 at the inner boundary and is 0 on the outer boundary. And now, what is the resulting displacement field? Well, we can look at lambda Lifshitz, and we can consult with the classical elasticity theory. So the free energy has a Lagrangian and a surface term. This is the traction, and this is the this is the tension. This is the displacement on the outer boundary. And the Lagrangian is nothing but half the stress tensor times the strain tensor. And in linear elasticity, there is a linear relationship between the stress and the strain. So this is the stress here. And the strain is related to the displacement in this way in linear elasticity. So now we have this Lagrangian, we follow lambda Lifshitz, we minimize the Lagrangian, and we try to find what is happening. So when you minimize the Lagrangian, the result is the famous equation, the divergence of the stress tensor has to vanish, and there are, of course, the boundary conditions on the outer boundary that the traction is agreeing with the stress there. Okay, in this geometry, the classical elasticity dictates if you have a radial thing, this equation translates to an equation for the displacement field, which is the simply the second derivative of the displacement, the first derivative, the zero derivative, all this has to sum up to 0. This is the equation that is easy to solve, and the solution is that the displacement looks like this. It goes to d0 when r equals r in. It goes to 0 when r is r out, and it has a form that looks like this. Okay, so as you're not surprised, you are inflating in the middle, so the most displacement should be there, and then it's going to fall as a power law in the bulk, but of course it's not a pure power law because it has a 0 boundary condition at the outer scale. So this is what you expect. Now let's look at some experiments and some numerical simulations. So here are some examples of measured displacement field in a classical glass former. And sometime you do this, and you see indeed the displacement field is really centered around where you are. And if you do now the radial average of this displacement field, boom, it agrees exactly with what classical elasticity is expecting. However, sometimes not at all. Sometimes you do the inflation at the center, and the displacement field is all over the place. It's not at all decaying as a function of the distance from the center, and it has wonderful shapes. It can go negative, meaning that things can go inwards even though you inflate it outward. It can have oscillations. It can have all kinds of things, and no elasticity theory in its known version can explain these things. So we need to think about what is going on. So let me explain what is going on. As I said, with strain on amorphous solids, you create quadrupolar local events of stress release. And these quadrupoles now, we need to take them into account in our Lagrangian. So in fact, our energy now is going to be the elastic energy, the interaction between the quadrupoles, and also the interaction between the quadrupoles and the elastic background. And now our theory has to take this into account. But by the way, we know this. We know this for a long time already, since a decade, because we were looking at the phenomenon of shear bending. But nevertheless, this has not been used in the form that I'm going to tell you until recently. So now I'm writing the terms here symbolically. So here's the gain is the stress times the strain, the same term that we had before. Then we had a new coupling to the quadrupole interactions, and we have a coupling of the strain, the background strain, with the quadrupoles that appear. Now we need to minimize the thing, and what we find is upon minimization of this energy, we obtain the same equations as before, divergence of sigma equals 0, but with the normalized elastic moduli. So this is the analog of electrostatic dielectrics. Dielectric, you put an electric field, you form dipoles there, quadrupoles here, and these don't change the form of the theory, but they normalize the moduli. As I say, this situation is analogous to dielectrics. However, now what happens if you have a large density of quadrupoles? You have a large density of quadrupoles, not only the density of the quadrupoles there, but there's a new ingredient. And the new ingredient is the gradient of the quadrupolar density. And the gradient, okay, the gradient of the quadrupole density is a vector, and of course this is a dipole. So now, once you have gradients, which you don't have, as I said before, I alluded before, majority of studies of amorphous solids are with simple shears. These don't create gradients. So in all our thinking, and I just give you one example, we are looking now at non-uniform strains, because then you create gradients and you create the dipoles, and you can see the transition between quadrupole and dipole phases. Okay, so in the presence of dipoles, the most general isotropic and homogeneous quadratic energy. And by the way, I'm showing you here nonlinear stuff, only to quadratic order. And you see that you have the usual thing. Now I'm already assuming that the elastic tensor has been already normalized by the quadrupole, so I don't need to show the quadrupoles again. But I have now the dipole term. So I have the dipole-dipole interaction and the dipole displacement. And now you need to minimize the new Lagrangian. And when you do this, you understand what you've seen before. Upon minimizing the energy, you get a new equation for the displacement field, and instead of having 0 here, you have a term that is proportional to the displacement. Now, this is totally new physics because this breaks translation invariance. Usually in elasticity theory, the displacement only appears with gradients. Here, the displacement appears by itself. So you think, wait a moment, if I take now my system and I move it, I change the displacement. It cannot be. No, but I have the boundary conditions which protect me. This is correct, and it means a broken translational invariance. You have a spontaneous breaking of translational invariance, and this is seen because this factor here is a inverse scale. So you create spontaneously an emergent scale. And now, if you do this in polar coordinates for the system I showed you before, then the equation before is modified. Now you have the kappa squared, which has to do with this thing here, which is the inverse scale squared, in fact. And this kappa squared appears here. Now, what is this equation? You all know. This is the Bessel equation. And with the Bessel equation, this solution is again analytic, and you can predict what is the displacement field. It's given in terms of the Bessel functions of the first kind, with the kappa acting as the length scale. And now the solution here can take all kinds of shapes. For example, here, it can become negative, can have oscillations, et cetera. And indeed, this is what we see. This is the reason for what I showed you before of displacement fields that are totally not expected in elasticity theory. Sorry. Here, that's emergent. That is emergent. It depends on the configuration, and it can change because of the amorphicity. It can change from configuration to configuration. Of course not. This is an emergent field, right? These are emergent. They are measurable, as I can argue to you, but they are not known a priori, and they depend. You do the same experiment twice with configuration that has been created independently, and these are different. And also the kappa is going to be different. Sure, but yeah. So these mu's appear in these things here, in this and this. So these are new moduli that are not existing in Lambda-Lifshitz, and they are going to change the kappa, and are emergent in the sense that it can change from configuration to configuration. Okay. Colleagues asked when we came up with this, but where are these dipoles? How can you show that they're dipoles? Okay, in electrostatics, it's trivial, right? I mean, because you can see that molecules get polarized and they're there. So this is a little bit of a technical slide, not as technical as many of the lectures that we had here, but nevertheless, let me show you quickly how it works. So these are two examples that we have looked at in which the displacement field is non-classical, that is anomalous. So once like this, and we want to show that indeed the dipoles are there. So the idea is that you look at the bi-Laplace equation, the usual bi-Laplace equation, which is usually 0, and you say, suppose that there are dipoles, then on the right-hand side I have a source, and if this is the case, I can now do integration over a boundary. You do the usual Stokes theorem, then you get that this integrated is the gradient of the pressure dotted into the unit vector on the boundary. And if this is the case, they can do this also on the right-hand side. So now this is the dipole here. So if this integral, which is the gradient of the pressure, you compute it and it's not 0, it means that the dipole is there and it's not 0. This is the usual thing like Berger's vectors, etc. And the pressure is the Young modulus times the trace of the strain. So when you translate this, you find that the condition on the existence of the dipole is that you have to show that the gradients of the divergence of the displacement, which is this is the function for the displacement. For the displacement, we call it integral 1. You can compute it explicitly. It's not 0. On the other hand, the gradient of trace u is from the equation that you have has to agree with minus kappa squared d. So you can also find another condition that the gradient doesn't vanish if kappa is non-zero, and the displacement field satisfies this. And indeed, when you do this we call the second integral that we can compute from the displacement field, and now you can compute I1 and I2, and indeed they are non-zero, and the ratio between the two has to be this kappa squared, so you can actually measure independently this kappa squared, and of course it agrees with the fits that I showed you before. So the dipoles are there. I mean, just to convince you that we can actually relate directly the functional form of the displacement field to the existence of the dipoles. Now what happens in 3 dimensions? As I said before, neither exotic nor Kosterlitz-Towles exist in 3 dimensions for the reasons I said before. Because either dipole for Kosterlitz-Towles doesn't have a logarithmic energy in 3 dimensions, or because simply hexagonal crystals don't exist in 3 dimensions. But now we have a situation that is different, in the sense that in our theory, if correct, it should extend smoothly to 3 dimensions, because the dipoles here exist only as the gradients of the quadrupoles. Now, there's no question that the quadrupoles are there. You see them in experiments, in simulations, the quadrupoles are there. There's a density of quadrupoles. There's going to be a gradient to the density of quadrupoles if the density is not too small, or if the system is not too uniform. And therefore, you would expect that the theory will go directly also to 3 dimensions. And if so, it'll be interesting, because it might be probably the first example of a Kosterlitz-Towles-like transition that you have in 3D. So what we do, I can show you numerical simulations. We look at spheres now, 3-dimensional spheres with little spheres of 2 different sizes that form an amorphous solid. And again, we take a little sphere in the middle, R in, and we blow it up. You inflate it. So you inflate a small sphere in the center. You equilibrate and measure the displacement field. Here's an example of a cut through the sphere. And indeed, the displacement field is no longer decaying when you go out into the outer boundary, which is what we expect in an anomalous case. And now you look at the displacement field, and the blue is the solution of the Bessel equation, the three-dimensional now Bessel equation we have in the theory. The dots are the data of the spherically averaged displacement field. This is one example. This is the other example. The phenomenon exists. Let us say we have, presumably here, a transition from quadrupole to dipole dominated anomalous elasticity, both in 2 and 3 dimensions. What about dynamics? This is actually work in progress. I'm not going to say much. Can you say the same thing also about dynamical fluctuations? So the easiest that I can think about is oscillatory inflation of this inner thing, either in 2 dimensions or in 3 dimensions, it would go oscillatory. And we tried a very simple theory in which the Lagrangian simply adds the rate of change of the displacement and the usual stuff we had before. May or may not be sufficient. We'll see. And indeed, when you look at numerical simulations, this is in 2D, you see that the displacement field has both in and outgoing things, so it's anomalous, and we're studying this, and I think that we'll see interesting results also for the 3-dimensional case, and the existence of the dipole-dominated phase will also be important for understanding the dynamics. Okay. In theory, what you do, you write down, you again use that Lagrangian, you find an equation for the displacement field. It has a solution that is the sum of 2 contributions. One is time independent and one is time dependent, and you can analytically solve this. I'm not going to go into detail. It seems to fit pretty well, but as I say, this is still work in progress, so I don't want to put a final line on the development of the dynamics. What about the beloved simple strain? So most of you are not familiar with this, but you know, as I said, the predominant stuff that people have done in amorphous solids, Sergio will tell you, is simple shear and pure shear, which I think is the worst thing that you can do to study phenomena of the type the times thing because of the uniformity. Nevertheless, when you do this in numerical simulations or in experiment, you find that in amorphous solids, the stress versus the strain is not a continuous function, but it has linear parts and then drops. So now, even though you're doing a simple shear here, and this is uniform, during the elastic increase of stress versus strain, nothing happens, but at the drops, you're no longer uniform. The plastic drops do what they want, not necessarily what you impose. And then I'm showing you here with the blue the calculation of the dipoles, and there is in fact a dipole appearing at every such drop because now that you are non-uniform. People didn't know about this. It has consequences. I'm not going to bother you with the consequences. I think this is a big issue for many people who are doing what they call elastoplastic models because they don't have this in the theory, they don't have dipoles, they don't have screening. So I think this will be discussed furthermore in the next few months. Okay, conclusions and open questions. So what did we learn? We learned that plastic events in amorphous solids act as screening sources, and one can encounter both quadrupolar and dipolar screening. Now, if correct, then I claim that doing theory without taking into this account is like doing electrostatics without knowing about the Debye. I mean, you have to take this into account because it's part of the physics of these solids and it's important. How you want to do it depends on you, but you have to take this into account. Now, one question that we are worried about is the transition sharp? So I showed you for sure we have a situation which is quadrupole dominated, and for sure we have situations which are dipole dominated. Now, as a function of parameters, pressure, interaction potential, I don't know, all kinds of things that you can think about, do you have a sharp transition? We don't know. That is to say, the simulations that, or the experiments or the simulation needed to do this are running. You have to do a lot of simulations and find a phase diagram. So this is still work in progress, we don't know. My expectation is that in 2 dimensions, it's certainly going to be sharp. In 3 dimensions, maybe it's going to be a crossover. I'm not sure, but this is an interesting question for the future. This is the simulations that I picked up from Ludovic Berthier of stress versus strain in a classical model of an amorphous solid. And you see the phenomenon that is known as shear bending. So you have here an increase in the stress when you increase the strain, and at some point there is an instability, and boop, you have a fall. What happens there, you shear, and suddenly all the shear is concentrated in a thin layer, and then the system slides along this thin layer, it's known as a shear band. And we would like to do a theory of this, and I think that the theory that we are developing is relevant, but we have to go nonlinear, because this phenomenon is an instability, and the instability needs a nonlinear theory in order to be understood. And in fact, how to explain this? We need to go nonlinear. And our question is nonlinear in what? Because there is nonlinear elasticity, which is an engineering subject that to me looks horrific, but it could be also nonlinear in the screening. As I showed you before, the Lagrangian that we've taken so far were quadratic, giving a linear theory, so you have to go to a higher order. It's doable, but has not been done yet. So there's a lot of things to do. Do we need to take into account nonlinear dipole screening? Possibly, but has not been done, et cetera, et cetera. So there's still many things to do, and I stop here, and I thank you very much for your attention.
Thank you very much, Itamar, for this very nice talk. So do we have some questions, Sergio?
Okay, go ahead. No. If you are young people, okay.
By the
no,
way,
so
here there is a second one.
Okay. So no,
Yes,
very interesting.
Thank you.
And now I have several questions
Go ahead.
about both the experiment and the numerical simulations. In numerical simulations, what kind of sphere do you have? Are they elastic spheres or just hard spheres?
No, not hard. So there's a soft sphere or Leonard-Jones. You know, we have many.
Okay.
So all that we have tried all the known models. You know, the Leonard-Jones, the inverse power, the soft spheres, and all this. Hard spheres are a limit that I don't like, I have to say, even though it is loved by the theorists.
Yeah.
But you know, it's only loved by the theorists because it agrees with theories in infinite dimensionality. You know, because in infinite dimensions, let me just say a word about this. I mean, you know, our friends, what I call the Parisi-Paris axis of evil, they have come up with a beautiful theory in infinite dimensions of jamming, for example. And they found exponents that agree with finite dimensional hard spheres calculations, which was a big surprise, because usually, you know, the infinite dimensional thing is sort of mean field, and you don't expect it to agree. The point is, of course, that what is the simplification in infinite dimensions? That you can cut off all the expansions above binary. So only the binary diagrams, binary collisions are important, because the probability in infinite dimension, the 3 particles will have the same coordinates in all the infinite coordinates is 0. So, okay. Now, hard spheres, the point is, they interact only when they touch, and the time of collision is 0. So the probability that you have 3-body interactions in hard spheres is also 0 in finite dimensions. So this is a fluke. Okay, it's an interesting fluke. It's a lovely fluke, but it's a fluke. Yeah. This doesn't occur with softer potentials.
No, of course, yeah. No, that's may continue because I was.
Yeah, go ahead.
The other, just comparing the experiment and the numerical simulation. you have shown that in the experiment, actually, you have events in which a system, standard elasticity works well, okay? And in the numerical simulation, that is it occur, and then if it occurs, what are the conditions?
Okay, so I will explain. I mean, maybe I didn't explain this well enough. Why we have these two types of behavior. Here, we did only one parameter change, which is the pressure. So at high pressure, the system is very brittle. So there's very little plasticity. There is plasticity, but you are in the quadrupolar screening thing that you have a renormalized moduli, but you don't change the form of the theory. When you go down in pressure, not all the way to unjamming, down in pressure, the system becomes more ductile, there's more plasticity, and then the gradients of the quadrupoles are important. You have dipoles, and then you have a change in the behavior which is fundamental. Now, as I said, an important question is going to be whether this transition is sharp or a crossover. That is an issue that we need to deal with, and we're dealing with. But this is what we did. Now, you may have a situation that you want to think there's more rich, in the sense that you can change not only pressure, you can change other parameters in your problem, and there can be a transition also because of that. You can change, for example, the amount of inflation. The amount of inflation, maybe for small inflation is going to be quadrupolar. For large inflations, you're going to make big gradients. And so the phase diagram is not trivial. And we're trying now to map it by doing hundreds of simulations and to really get a phase diagram. A phase diagram is going to be akin in some way to what Sid Nagel did for jamming, you know, where they had a J point, which actually doesn't exist, but still it was very useful to have the full phase diagram drawn for people to focus on what is happening. So we're trying to do this also here. But that is the area fraction. The area fraction, which is proportional, which depends also on the pressure, right? I mean, you can choose, yeah, the area fraction. Yeah, they have disks of two types, and you can change the area fraction. When the area fraction becomes larger, you get high pressure, and you get quadrupolar, and then you get. Thank you for asking this, because maybe I wasn't clear enough. Yeah.
Itamar, we have a question from Benoit Dousseau on the chat.
Okay.
So in Kosterlitz-Towless theory, a key variable is the vortex fugacity. Do you introduce such fugacities for your dipoles and quadrupoles? Yes. And how do they enter your effective free energy?
Right. So this is precisely what we do. You know, you call it vortex, I call it dipoles. It doesn't matter, right? I mean, so we have a density of quadrupoles, a density of dipoles. They enter into the Lagrangian. Of course, I wrote things in a symbolic fashion. You need to really put in how the interactions behave in order to do a computation, but it's not very different in the sense that the only thing that I can say is that we have done so far only quadratic order, so the theory is linear, whereas people have looked in hexatic and other things also on nonlinear and on linearization group and all kinds of things like this. Massimo.
I understand the shear is not the ideal setup, but I've not understood why you said that you don't produce gradients. Because of the amorphous nature, you do produce gradients.
Not really, because when you do a long-range uniform strain, okay, then you create these dipoles.
So you do create.
You create dipoles,
yes.
But you create dipoles, but they're sort of uniformly organized. Only when you have a plastic drop, this spontaneously makes a strain that is not uniform, and then I see the dipoles.
But you don't create them by fluctuations? You cannot create them
Zero temperature. This is zero temperature. Remember, this is not a usual hexatic or constant solids. It's not temperature dependent. These are solids, and you can think about the temperature as being zero for all practical purposes. And therefore, fluctuations are only, I wouldn't say fluctuations, I would say disorder. There is
no, but
disorder.
the disorder, what I mean by fluctuation is the local disorder in the
yeah. This is precisely what we're talking now with Giorgio about how to do a theory taking into account the disorder as an equivalent for the temperature in other stuff. But this is still working
but you do expect to create.
You may so far in the simulation people have used, the simulations are relatively small. Okay, you have 10,000 particles, 20,000 particles, 50,000 particles, that's already a lot. And we don't see gradients during the elastic stages. Only when it drops, whoop, it comes up. And you can measure it. So we can do these integrals that I showed for the dipoles at every step. 0, 0, 0, 0, and then the drop, and whoop, there is a dipole.
But the drops are telling you that there should be.
Quadrupolar.
Yeah.
The drops themselves are creation of quadrupoles. But now, once it drops in a way that it wants, which may be exerting a non-uniform strain, and then dipoles appear. So it's a delicate issue.
Yeah, so there was already a question actually about the core energy of about the core energy or the fugacity of the defects that you call dipoles and quadrupoles, and that are called discriminations and dislocations. And it's known actually that in a disordered system, this core energy is a random variable. Actually, you have a broad distribution of this core energy. And I didn't see actually this broadness, this distribution entering as a parameter in your theory.
It appears through the coupling tensors that appear in the Lagrangian, which change, indeed, I wouldn't say randomly, but in a complex way from from one configuration to the other. So all these terms are actually emergent. I cannot tell you a priori what is going to be the coupling tensor to the QQ and to the PP or to the PD thing, because these depend indeed on the random amorphous situation.
And can you characterize the statistics of this tensor?
No.
So I have
Yeah.
So I have a related question. So it's very naive. I know nothing about elasticity, but when you show us the displacement field, they are not at all rotationally symmetric. But the theory you develop is rotationally symmetric. So what does it mean?
It means that the theory is not yet complete. And indeed, you know, what we find out when you do inflation, even very small, without even creating plasticity, all the Michel solutions, the famous Michel solution from the 19th century, which are Fourier modes, not all, the lowest order are excited. So there is azimuthal dependence that we didn't take into account, we didn't study, we didn't write equation for. We can do. You know, it's with the same effort, you can also do a theory for the d theta, not just the dr, not just the radial part, but also the angular part. We still didn't do it because we're still fighting with referees that don't want to hear about this. So, lines up. You know.
So if the phenomena is statistical and if you have this, so how do you check your theory? How do you falsify it? Do you need to really have a statistical theory to be able to?
You know, we have a theory, we have a simulation, we have experiments, and we just compare. And the profile of displacement field that were surprising and unexpected fit very well with the profile that appear from the theory, but with a fitted parameter kappa. So the symmetry breaking parameter kappa, I don't know yet how to predict it a priori from, say, the knowledge of the amount of disorder. So there's a very important thing, you know, and also coming back to what Sergio said, there's another parameter, which is degree of disorder, right? Which we are now studying systematically. That is to say, we are looking now at systems with increasing disorder to see also whether the transition is sharp or not. So there are many parameters here that can determine the numerical value of the symmetry breaking and the new tensors that appear in the system, and we still don't have a full theory. So we're still at early stages. This is what I said, that there's still a lot to do. It's really an open issue. Yeah.
To go back to your last statement, Are there, for example, in numerical simulation or in the experiment, some precursors of the formation of these quadrupoles? I mean, a priori, I observed in the sample, or in the numerical simulation probably easier, something that tells you that the quadrupole will form there and not in another place.
So the question is interesting. They are studying. I always forget that I need the speaker. So the question is very interesting and has been understudied by a number of colleagues, including us. And what you can do when you create the system, at least in numerical simulations, you have the Hamiltonian of the system, you can compute the Hessian, you can look at the Hessian and its eigenvalues and eigenvectors. And you find that there are indeed localized modes, and these localized modes are indeed sort of quadrupolar. They don't express themselves at zero strain, but when you increase the strain, the eigenvalue associated with them is going to zero, and when it hits zero, boop, you get the plastic event. So it's there, right? It's in the structure, but you need to be circumvent in order to see this, and you only can do it when you have the Hamiltonian and the Hessian. It's very difficult to do it in an experiment, as you can imagine.
So thanks a lot, Itamar.
Thank you.
Very nice talk.